and 15 in a second here. Okay, so the question was, can we look at some of the limit questions with trig involved? And that would be something like 14 and 15. So if you look at number 14, it says the limit as x goes to pi of 3 cos x over 5. So we know that all we have to do to get started is plug in pi where we see an x. So we get 3 times cosine of pi over 5. And the calculator can do cosine of pi for you. So if you wanted to type this into the calculator, you really just have to make sure that you're in radian mode, because if you're not in radian mode, it's definitely not going to tell you the correct value for cosine of pi. But without having a calculator available to you, let's say, how else would you do this? Pi is a quadrantal angle. Okay, so pi would be, at this point on the unit circle, the coordinates at that point are -1, 0. And I know that cosine specifically goes with the x value there. So once I have all that established, I know that cosine of pi is just -1. So 3 times -1 over 5 should be -3/5. So when you're doing a limit question, I'd like you to show some work that goes with that. And I think this is really, sufficient work to get that algebraic, result here. But you can check things on the calculator. You can certainly, maybe just do that trig part on the calculator. Similarly, for number 15, the limit as x goes to 0. If you plug in 0 for x, you're going to get sine of 0 plus pi over 2, which is really just sine of pi over 2. And maybe I'll even just steal the picture from over here. Pi over 2 is up here, right? Coordinate is 0, 1. Since sine corresponds with the y value of that point, the answer to number 15 is actually just 1. So it's been a while since we've done some of this trig evaluating. But what I'll tell you is trig evaluating kind of in general is a pretty important step in, let's say, being successful in a calc course that you might take next year. So you'll see some more of this start to come up again. So I'll challenge you to maybe look back at some old notes when you're doing these questions if you need some help. But otherwise, calculator can do it for you too. Something that I've heard from area colleges, and this was not my experience at good old Geneseo, but some colleges don't let you use a graphing calculator. Like I feel like I heard from a Brockport class once that they're not allowed to use the calculator, which is a little, I know at times this year I've made it such that you couldn't use the calculator on certain tests, but for the majority I feel like we've been able to use it. So just kind of be aware of that anything we can do without a calculator, your college might require you to do that next year, depending on where you are, and I guess who your professor is. So Addie, that was a really good question. What else can I help you with from the limits review or otherwise? While you're thinking carefully about your questions there, during our awkward Google Meet pause here, I'll show you just the bottom half of this section. All have limits as x goes to infinity. Does anyone want a quick recap on what do we do for limits as x goes to infinity? A little bit different than plugging in as x approaches a numerical value. I'm not seeing any yeses in the chats or people jumping up in excitement over limit as x goes to infinity. Okay, so I will go to, is there anything that's really jumping off the page from the limit applications review that you'd want some practice with? It's really all the same concept for each of these. Find the derivative. And by the way, when you find the derivative, f prime of x, I'm expecting you to use the limit definition. So it's the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so you're going to do that for each one of these to get started. Then find the equation of the tangent line at the given point. Remember, this gives you the equation for the slope of the tangent line. So then you plug in these values of x to get the slope. You use that point in point slope form. Okay, so you don't have to convert to y equals mx plus b or anything like that. And then determine any points where you have a horizontal tangent line. That's if there's any solutions to when the derivative equals 0. Horizontal tangent line would be when the slope of the tangent line is 0. So you'll solve that for x, and if there is a solution there, plug it back into the equation to get the y value that goes with it. So that's the main idea behind this review. While you're looking at numbers 1 through 8, is there any that you'd like me to model with you now, such that you'll feel like, yep, I'll be good to go when those come up on the test?
Are there any that you feel are like particularly hard, like compared to the others?
That is a good question, Addie. And I saw that I think technically we do number 7. Was that the one you said? Number 7. Yes. Okay. I'll do number 7 because I like that one, Emma. I think that's a good one to check in on as far as when you have a radical in the equation. That can be a little bit tougher for students. The one that I think is maybe a little bit challenging is something with x to the 4th. And the reason why the one I think x to the 4th is challenging, we haven't done any like it in practice, is that it doesn't look so scary when I just plug that in to the definition, right? So it would be x plus h to the 4th minus x to the 4th over h. But this is actually a somewhat complicated algebra for us to do. I shouldn't say it's complicated, it's just a little tedious. We've done x cubed a few times, and I would almost just have you memorize that if you do x plus h cubed, you're going to wind up getting x cubed plus 3x squared h plus 3xh squared plus h cubed. I think that's the best way to go if you ever have an x cubed in your example. But for x to the 4th, that one's a little bit tougher. I guess what I could do is I could take what I have for x cubed and then multiply it by one more x plus h quantity. So I'll write down what the expansion of this looks like if I do that, but that would be like kind of a lot of box method multiplication or foiling or whatever you want to do off to the side. So this would be x to the 4th plus, it would be a 4x cubed h term plus 6x squared h squared plus 4xh cubed, and then finally at the end plus h to the 4th. And if you're wondering, like, Mr. All, how did you know that? There used to be in Algebra 2 a topic that was taught called binomial expansion. And that's what I'm doing. I'm taking a binomial, raising it to a power, and this is what the expansion of that looks like. So there are definitely patterns that exist when you expand binomials of this form. And it actually has something to do with, I know you guys didn't want like an extra math lesson on top of everything right now, but if you've ever heard of something called Pascal's triangle, which looks something like this, what I'm doing is I'm adding the numbers in between to get what's going on in the next row here. So like 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6. There's kind of ones building along the outside here. Notice how these are the coefficients for x cubed up here. And that these are the coefficients for x plus h to the 4th. So knowing something about Pascal's triangle actually makes the process go much faster, which is nice. Hopefully that helps for maybe something like 5, where just the expanding part would be tricky. I will do number 7, and then while I'm working on 7, again, maybe think of any last-minute questions you might be wanting to go over. Because if not, we'll kind of do our last Google Meet check-in here. Okay, so here's what the process is going to look like for number 7. The first thing you're going to do is find the derivative in part A, which is the limit as h goes to 0 of the square root of 1 plus. I have to replace that x with the quantity x plus h. So maybe right from the start, I'll distribute the 2 in and make it 1 plus 2x plus 2h minus the function f of x all over h. And when you do a definition of derivative, you'll never be able to plug in 0 for h right away and evaluate the limit. It's always going to become 0 over 0. So you have to do something algebraically to fix this. Whenever it's an example with a radical, the fix is multiplied by the conjugate. The conjugate is the same thing as the numerator, except with a plus sign in between here. So it's going to be the square root of 1 plus 2x plus 2h plus radical 1 plus 2x. What students commonly forget to do for this question is also, maybe they remember to multiply the bottom by that as well, but they forget to write it in the next step. Okay, so in this next step here, I'm going to go ahead and say it's the limit as h goes to 0 of, when you multiply these two things that are conjugates up at the top, you really just have to do the first terms and then the last terms. So the first terms, if I multiply those, the radical just goes away. It's 1 plus 2x plus 2h. Then minus the product of the last terms. It's the quantity 1 plus 2x. This is going to be all over h times the conjugate. Don't worry about distributing that h in. Remember that that h on the bottom actually is going to have to cancel with an h on the top, hopefully, if I've done the algebra correctly. I would like you to continually write limit as h goes to 0, because that's actually the most important part of what we're doing right now. Taking the limit as h goes to 0 finds the slope of the tangent line, what we're looking for there. So I'm going to distribute that negative sign in to make it a -1 and a -2x. It's maybe another little area where we might make a mistake. I know it's a little tedious to rewrite that whole denominator, but okay, now that I have that, notice how on the top we've got 1 and -1 that cancel. We've got 2x and -2x that cancel. So I'm going to cheat a little bit here. And what I'm going to do is, although I would actually like you to rewrite this in another step, I'll allow you to, in this step, cancel these h's right here. So the h that's on the top and bottom would now cancel from this last remaining term. So you're taking the limit as h goes to 0 of 2 in the numerator over radical 1 plus 2x plus 2h plus radical 1 plus 2x. All right, now you're at the stage. Once those h's cancel top to bottom, now you can plug in 0 wherever you see an h, right there. So if I plug in 0 for this h, this whole term becomes 0, and this becomes 2 over radical 1 plus 2x plus another radical 1 plus 2x. And although that's technically a correct derivative, you would most likely see in a lot of instances this be simplified a little bit further. So this would become 2 over 2 radical 1 plus 2x's. And then, of course, the 2 on the top and bottom can cancel out. So the derivative, part A, should say that f prime of x is equal to 1 over radical 1 plus 2x. So I guess that begs the question, could I just say that the derivative is always, 1 over this radical quantity? And the answer is, unfortunately, that's not always the case. You do have to go through the process. Are there little tricks to finding derivatives? In a calculus course, you'll learn them. But the trick is not just putting 1 over the radical function. It would be nice if it was. It's a little bit more involved than that, but it's almost coincidental that it just works out that way. All right, part B says we're going to find the equation of the tangent line at 4, 3. So the first thing you have to do is you have to plug in and find the slope of the tangent line at x equals 4. Okay, that's what this notation represents. So 1 over the square root of 1 plus 2 times 4. So what that makes under the radical is it makes a 9 under there. 1 over radical 9 is the same thing as 1/3. So if this is the slope of the tangent line and it contains the point 4, 3, your equation would be y minus 3 equals the slope of 1/3 times x minus 4. So there's your answer to part B. And then finally, the part C says any points where you have a horizontal tangent line. So for that part C, you always just take your answer to part A, set it equal to 0, and solve. What you'll see in this example is if you try and solve for x, you would maybe multiply both sides by that radical quantity, right? And you're going to wind up getting that 1 equals 0, which doesn't make sense. So there's no points on this graph where you would have a horizontal tangent line at all. If you get a solution, so let's say there is actually a solution when you go to solve for x, you then take that x value, go all the way back to the original function and plug it in here to get the y value that goes with it. And you'd write that as a coordinate point. So if there is a solution, like I was saying, take that value of x that you found, plug it into the original function, not the derivative, and that will give you the coordinate where it has a horizontal tangent. So why doesn't this one have a horizontal tangent? A radical function looks like this. So if I pick a point on the graph, no, that's not horizontal, that's not horizontal. It's going to definitely start leveling out, but it never will become completely horizontal, which is why this equation winds up getting no solution there. Okay. So Emma, I'm glad that you asked that one because I think radicals can be a little bit tougher to work your way through, but hopefully now with this as a model, you guys should be able to work with any radical that may come up on that test. And I just get the feeling that there's going to be one, so. Okay. Is there any, that was kind of took me a little while to get through. Was there anything else that came up while I was working my way through that? Something else that you've thought about? Okay, I'm going to, if something comes up, that's fine, but I'm going to stop recording. It seems like we're kind of